In some cases, the electrons, the pair of electrons which constitute our covalent bond are equally shared, but sometimes they're not. And where we got to was getting to this idea of electronegativity, which is a way of determining to what extent the electrons are not evenly shared between the two atoms in the covalent bond. And so the electronegativity is a number. These are the numbers. You do not have to know the numbers. We would always give you the numbers if you need them. But this is what they look like. There's some nasty calculation you can do to work these out. But the important thing, the thing which you kind of need to get, is that the most electronegative element is fluorine. Right? It has the biggest number here. It's almost 4. And electronegativities get smaller as you go down this way, and they get smaller as you go across this way. Right? So the closer you are to fluorine, the more electronegative you are. And so the more you're going to want to have the electrons for yourself in a covalent bond. Right? Obviously, even if you're the molecule F2, then that covalent bond will involve the electrons being evenly shared, because both the fluorines really want the electrons, but they really want them the same as each other. So you end up with like a stalemate and the electrons are shared. But if you have a bond between, say, a fluorine and a silicon, then there's going to be a big degree to which those electrons are not evenly shared between the two, because the electronegativity of fluorine is much bigger than that of silicon. Hello?
Can you have a completely covalent bond between two different atoms?
A completely even sharing.
Yeah, what I always call it covalent.
If you had like you could come up with a couple whose numbers were basically the same. And in those cases, like carbon and hydrogen, right? Hydrogen's 2.2, carbon's 2.55. Those are close enough that we would consider those bonds to be nonpolar, so evenly shared, right? There is a cutoff. It's something like a difference of 0.8 or 0.9. We're not going to get into that sort of detail in this course, but yeah. Okay, so then if you have a bond between two elements which have different electronegativities, and I suppose that could read different enough electronegativities, because there is a difference below which it doesn't really matter. But if they have different electronegativities, the electrons in that covalent bond will tend to be more at one end of the bond than the other. They'll tend to be at the end of the bond which has the more electronegative atom at it. And what we find is that because electrons are negatively charged, if the electrons tend to be at one end of the bond rather than the other, and that end is the end with the most electronegative element in it, then that end of that bond will have a slightly negative charge compared to the other end, right? The electrons are negatively charged, and if they tend to be on one end rather than the other, then that end will have a greater negative charge than the end where they're not at. Yeah? And so if we had a bond like this, a bond between an H and an O, which have quite different electronegativities, then we wouldn't tend to draw the electrons right in between them like this, and the orbital that those electrons live in, we wouldn't draw as being symmetrical like this, but instead we would be tempted to draw it like that. And to be fair, that's not supposed to be two bulbs, just because I don't know how to do fancy pictures in PowerPoint. But the orbital tends to be bigger at the oxygen end than the hydrogen end, and the electrons tend to be much closer to the oxygen than to the hydrogen. And so because the electrons tend to be closer to the right-hand end, in this case of this bond, this end is the one that has the slightly negative charge compared to the other end. And so we have these little symbols to indicate that, right? It's not going to be a whole minus and a whole plus like you would with a cation and an anion. That's what you get if there's complete transfer of an electron from one thing to another. This isn't that. This is just electrons being shared, but shared more one way than the other. So it's not a whole charge, it's a partial charge. Say it's half a charge, 60%, 72%, something like that. And we indicate that like this. This is a little Greek d, which means a little thing, right? So this is a little minus charge, or a partial minus charge. This one here, the little delta plus, is a partial positive charge. Okay? So that's different to plus like you put on Na plus, and it's different to a minus like you put on Cl minus. It's just a partial charge, which is there because the oxygen is more electronegative than the hydrogen, and so it's pulling those electrons towards itself more than the hydrogen is able to. Yeah? We happy with that? And so if we have bonds which are like this, where you have one atom which is more electronegative than the other, and that causes there to be these partial charges present in the bond, we call those sorts of bonds polar bonds. Right? Or if you like, polar covalent bonds. Right. Now, one more Lewis dot diagram before we move on to something else. Let's think about O2. If we want to draw a Lewis structure for the molecule O2, then first of all, like we've done before, we want to work out the electron configuration for oxygen. And as it was before, it's 1s2, 2s2, 2p4. And so if we want to then go about trying to write a Lewis diagram for this, and we do it the way that we've been doing up till now, we'll say we've got two atoms, we want to make a bond between them. That means we're going to need one electron from one of the oxygens and one electron from the other oxygen to make our covalent bond. And so if we do that, if we draw out our oxygen, here's an oxygen with 6 electrons around it. One of them is being used to share with the other oxygen. If we do that, then these 2 electrons in the middle can form a covalent bond, but we have a problem. And the problem is that when we do this, each oxygen only has a share of 7 electrons. Right? The 6 that it started off with, plus the 1 that it's sharing with the other oxygen. And that's going to be a problem from 2 points of view. One, it's not going to be good from the point of view of the stable octet rule. Because remember, atoms try and get themselves into molecules so as to have 8 electrons around them, if they can. This is only 7, so that's no good. Yeah? Patience, patience, patience. See, there's a big gap over there? The other problem with this is that each oxygen now has an unpaired electron on it. And unpaired electrons are another way, well, I suppose they're a consequence of the fact that you've not got the stable octet. Those sorts of molecules are what we call free radicals. Right? So if you have an atom or a molecule which has an unpaired electron on it just sitting there, they tend to be very reactive, and if you get them into you, they will react with the first thing that they see and cause trouble. So these molecules are not very stable with unpaired electrons. So this can't be the way it is, because you know that O2 is stable, right? Hopefully. It's not all exploding in the atmosphere around you. So it can't be like this. So instead, what we can do is this. Instead of just going with one covalent bond by sharing one electron from each of the 2 oxygens, we can share 2 electrons from each of the oxygens. And so now, in total, we're sharing 4 electrons between them. And so 2 pairs means 2 covalent bonds, and so we would write this like this, where the oxygen has 2 lines between it, indicating that this is an oxygen-oxygen double bond. And now if you look at each of the oxygens and you do a count up of how many electrons there are around each of the oxygens, you find that they've both now got 8. And so they're happy. Everything's paired up, stable octet rule applies, everything's good. And so double bonds are pretty common. You can also get triple bonds under certain circumstances. You can also get quadruple bonds, unless we've finally decided they don't exist anymore. I know when I was a student there were quadruple bonds, and we got taught about them and how to work out what molecules did quadruple bonding and what didn't. But it was always a bit controversial, and I think maybe people have decided it doesn't exist anymore now. I'm not sure we're never going to worry about quadruple bonds, and we're probably not going to worry about triple bonds like this, right? But it's the same idea. You have a triple bond when you need to share 3 pairs of electrons in order to satisfy the stable octet rule. Yeah? Okay. Lewis dot diagrams tell us something about the numbers of bonds and pairs of electrons around the central atom in a molecule. So it's a way of counting up the electrons, so which gives you a way of working out how many bonds, and if you like, what sorts of bonds you would expect there to be in the molecule, right? But one thing that Lewis dot diagrams do not do is tell you about the shape of the molecule in 3 dimensions. And you are certainly going to see this in 191, but if you go on to do any sort of science that even remotely involves chemistry, then at some point you're going to come across this idea that the shape of the molecules is key to the way that they behave in, for example, your bodies. Right? If you go on and do pharmacy or pharmacology and that sort of thing, it's all about the shape of the molecules and how those molecules with a particular shape interact with other molecules of particular shapes to do certain things. Right? It's everywhere in chemistry, it's everywhere in biology and biochemistry as well. And Lewis dot diagrams are useless for telling us about shape. The thing that helps us with that is something else which is almost as old as Lewis dot diagrams, but is still a very powerful way of trying to work out the shapes of molecules. There are better ways now, well, there are more complicated, more detailed, more mathematical ways now, but most of the time they don't tell you anything that VSEPR theory won't tell you itself, right? So VSEPR theory, VSEPR stands for valence shell electron pair repulsion theory. Okay. As its name suggests, VSEPR theory is about considering the repulsions between pairs of electrons, bonding pairs and lone pairs, in the valence or outermost shell of the central atom of the molecule. Right? So the Lewis dot diagrams in general will have a central atom with some other things attached around it, and there'll be a certain numbers of pairs of electrons around that certain atom, right? And oftentimes that'll be 4. It wasn't for O2, but for water and for methane, there were 4 pairs of electrons around that central atom. So VSEPR theory says that if we think about how those 4 pairs of electrons will repel each other, that will give us an indication of what the resulting shape of the molecule will be. These pairs of electrons, the electrons are negatively charged. Again, if you accept that they're happy to be in pairs, but those pairs will repel other pairs, then it follows that the most stable shape that your molecule can be will be the one where those pairs of electrons, which are repelling each other, are as far away from each other as they can get. Right? If they don't like being close, then the most stable shape for the molecule will be the shape where those pairs of electrons are as far away from each other as they can be. And so the shape that the molecule ends up being will be directly related to how many pairs of electrons the central atom has around it. Yeah?
So is that repulsion within the pairs or between the pairs?
Between the pairs. Right? So like in the methane one, you had 4 pairs. So it's a repulsion of that pair with that pair and that pair with that pair, not within the pairs themselves. There's weird physics that means that the 2 electrons like being together, but only in tubes. Yeah? It's like wood pigeons. Yeah? Okay. So if there are 2 pairs of electrons around your central atom, this is a type we haven't seen yet, but if there are 2 pairs of electrons around the central atom, then the easiest way, for the way that those electrons get as far away from each other as possible is if they're on opposite sides of the central atom. Yeah? So the angle between them is 180 degrees. Hopefully that's relatively obvious. Yeah? They want to be as far away from each other as possible, then they're going to be 180 degrees apart on opposite sides of the central atom. And so we have a name for all these different shapes, and this name, the name for this one is linear, or as one of the lecturers here used to call it, linear. but he was Danish, so maybe that was his problem. So linear, and here's a little picture, which is a bit dark because this whole screen's a little bit dark. I must try and fix that sometime. But anyway, hopefully you can see there's a little linear molecule with a central atom and then two on the outsides, and it's 180 degrees. Those two covalent bonds away from each other. Yeah? And like I say, hopefully this is all in that handout that has come around. If you have 3 pairs of electrons around the central atom, then the best arrangement is for them to be 120 degrees away from each other. Right? You can sit and think about this quietly over a beer sometime if you want. I think this was all sussed out by the Greeks about 2,000 years ago. But 120 degrees away from each other is the best arrangement. They're the furthest away they can be. And so that one is called trigonal planar. So here's an example of a trigonal planar molecule, BF3, a boron with 3 fluorines attached to it. That molecule is trigonal planar. Those angles are 120 degrees. And it would look something like this. Yeah? So that's if you've got 3... Hello?
Do we know the angles because we had to write them in school?
Of course you did. What do you think?
Personally, I don't think so. But
Well, based on everything I've said so far this week, what do you think?
yeah.
I'd say no, you don't need to know the angles.
So how come you're explaining the angles?
I'm just telling you the way they work. I don't expect you to memorize them, though. Yeah. The numbers, and then when we get to bent ones, and it's really 104 rather than 109, I don't really care. From a point of view of Chem 191, which is, I think, for most of you, the initial first sort of focus, none of this is even in the course. So we're not going to ask you this stuff. It's important you understand all this, but we're not going to test you on it in first semester. Yeah. So the most interesting case is when you have 4 pairs of electrons around the central atom. So this is what we had for water and we had for methane. In this case, the best arrangement is if the electron pairs are at 109 degrees away from each other. And if you have 4 things 109 degrees apart from each other, then the shape that you get is called a tetrahedron. And so here's a picture of the methane molecule now in 3 dimensions. This, if you haven't come across it before, is this little sort of system that we chemists have for trying to draw molecules in 3D. If you just have a line like this, that is indicating a bond which is in the plane of the board. So these two are in the plane of the board. This bond here, which has got kind of a filled-in wedge pointing to the hydrogen, is supposed to imply that this bond is coming out towards you. And this one here, where you have all these little lines, the so-called hatched wedge, this is supposed to indicate that this carbon-hydrogen bond is going away from you into the board through, where's that? Outside somewhere, right? All of those angles between the CH bonds are 109 degrees. And the little 3-dimensional picture looks like that, right? This is very, very common. And one thing that you will see in Chem 191 in all the organic chemistry is you'll talk a lot about tetrahedral carbon atoms. These are all cases that we looked at so far where all the bonds are, all the electron pairs are bonding pairs. If you have a molecule where you have a mixture of bonding pairs and lone pairs, then these same rules apply, but we give the resulting molecule different names, right? So for example, if we have a molecule which has 4 pairs of electrons around the central atom, but one of those is a lone pair, and so there's no bond to another atom that those electrons are involved in, then we don't call it tetrahedral, because tetrahedral is a molecule which has a central atom and 4 things attached to it. If you have a molecule that's got a central atom and 3 things attached to it, and then a lone pair up the top, the angles are still going to be roughly 109 degrees because the shape is still roughly a tetrahedron, but it's not called that, it's called a trigonal pyramid. And so here's a trigonal pyramid, and that little red thing on the top is supposed to be the lone pair. It's not a very good picture. It's a bit frantic. But that's kind of what we're talking about, right? So it's like a tetrahedral molecule, but with one of the things taken off. What you've got left behind we call a trigonal pyramid. And again, this is on the handout. And if we have 2 bonding pairs and 2 lone pairs, like we do in water, then again, because the central atom's got 4 pairs of electrons around it, the shape is based on a tetrahedron, but we don't call it tetrahedral, we call it bent. And so here is a water molecule, if you like, with a bent structure. And again, the little antler things are supposed to be the lone pairs. Right? So those angles are roughly 109 degrees. They're not exactly, but I don't think we need to get into that for the moment. But the shapes have different names depending on how many covalent bonds there actually are in the molecule. Does that make sense? An important consequence of these shapes is that in some cases there ends up being more electrons on one side of the molecule than the other. So here's a little molecule here. Let's imagine this is ammonia. We're going to come back to ammonia in a minute. So we've got nitrogen in the middle. We've got the green things are 3 hydrogens, and then that's got a lone pair of electrons. What that means is that because you've got electrons at the top that aren't being shared with anything, the top of that molecule we can think about as having a partial negative charge, just like we did with our OH bond earlier. So with the OH bond, we said that that was a polar bond. For these sorts of molecules, we can say that the whole molecule is polar because it's got this lone pair of electrons at the top that isn't being shared with anything else. Yeah? So you end up with more unshared electrons at the top than at the bottom, and so overall you would say that that is a polar molecule. In the same way, you would say that water is a polar molecule because, see, if you look at it like from this way, the top here has got extra electrons and the bottom doesn't, because those electrons are shared with the hydrogens. So water is a polar molecule, and ammonia, which, you know, if you like, is that one there, is a polar molecule as well. We're going to come back, in fact we aren't. The lecture that Kiri's going to give you when I'm in Wellington is going to be all about the consequences of polar molecules and how that affects their behaviour. So that's week after next. All the covalent bonds that we've seen up till now have involved having 2 atoms which each have an electron, and those atoms come together and they share their electrons with each other to make a covalent bond. If you're oxygen, then you come together and you share 2 of your electrons with another one to make a double bond. But in all cases, you start off with atoms that have electrons and they come together and share their electrons with each other. Sometimes that is not the case. Sometimes you get a covalent bond formed where one atom has no electrons and the other one has 2, and the atom with 2 electrons shares both of them with the atom that has none. Yeah? So you end up with a covalent bond because you end up with 2 atoms which are held together by sharing a pair of electrons between them, but both of the electrons started off on one of the atoms rather than them bringing one each to the bond. And so this type of bonding is called coordinate covalent bonding. You may have heard it called dative bonding. Did anyone get that at school? Yeah, that's kind of an older way of saying the same thing. Coordinate covalent bonding is what you'll see here, and it is commonly found in particular types of molecules called complex ions or coordination complexes. Again, complex ion is kind of the school word. Coordination complexes is the university version of that, right? So these coordination complexes are compounds which are put together using coordinate covalent bonds. And so what you often find is that the atom which has no electrons in these particular bonds is quite often a transition metal ion. So these are the ones that live in that middle part of the periodic table along the sort of the long bit, about halfway long. So for example, copper. Copper is a transition metal, and so one of its characteristic chemical properties is that it forms coordinate covalent bonds. That's what pretty much all of those transition metal ions do. It's one of their key things, is that they like to form these coordinate covalent bonds, but they are always the one that doesn't have any electrons. They always have to form these bonds with something else, where the something else is the one that has the 2 electrons, right? And so in the lab you're going to do this afternoon, the other thing which has the electrons which it can use and bring to make this coordinate bond is going to be ammonia, NH3. And if we were to do a Lewis dot diagram for NH3, it would look like this, right? Using all the same sorts of ideas we've already talked about. Hydrogen's got 1 electron, nitrogen's got 5 valence electrons, and so you can come up with a Lewis dot diagram like this, where 3 of the nitrogen's electrons are used to share with the hydrogens to make 3 normal single covalent bonds, and then the nitrogen ends up with a pair of electrons, a lone pair, left over, right? In total, that nitrogen's got 8 electrons around it, so it's happy. It's a perfectly little stable molecule, but smelly, but it's stable. But it's got this lone pair of electrons, and it's those that it can then use to make a bond to the copper. We can draw a little picture like this. Okay, so here's our copper, and here's our ammonia. And normally, at this point, one of these dots here would be blue, and one would be black, yeah, because one of them would normally come from one thing and one would come from the other. But here they're both black because both those electrons come from the nitrogen, from the ammonia molecule, and neither of them come from the copper, right? And so by doing this, you can hopefully see that it's not actually stuffing up the stable octet rule as it concerns the nitrogen, because it's still only got 8 electrons around it, yeah? So this is happy. And so this bond that you would make here is what we would call a coordinate covalent bond. Now, of course, one of the things about these coordination complexes is that you don't just get one bond to the copper. In the case of this one, you get 4. And so the copper ends up having 4 of these ammonias stuck to it like this. Now, the reason why the copper has 4 bonds is something that you need not concern yourself with. Because depending on, if you were to replace ammonia for water, then you can put 6 waters on a copper. You can only put 4 ammonias, and there's all sorts of other rules that determine how many bonds transition metal ions can make that are sort of third-year chemistry. Right? So this is not something you need to worry about. If you need to know how many bonds the metal ion makes, we will tell you. Okay? And then finally, we call molecules like the ammonia in this case. Oh, sorry, yes.
What happened to the copper's like valence electron? Or does it not have any?
Yes, it does. They're doing something else.
Cool.
Does anyone have a feel for what colour this compound would be? Go on, say it. All this level 2 stuff that gets drummed into you, it's blue, yeah? Actually, it turns out this is purple. But nonetheless, it's kind of a bluey purple. The valence electrons on the copper are busy making the compound blue in a way that we're not going to get into in this course at all. So it definitely has valence electrons, but they're not involved in doing this. They do something else. Okay, so the ammonium molecules in this case, the ones which have the pair of electrons which they can use to make a bond to something else, when the other thing is a transition metal ion, these are called ligands.